Now we're going to define the diameter of a set. So if E is a subset of the real numbers, then the diameter of E is the supremum of, you take any 2 points in E and you take the distance between the two, and then the diameter is just the supremum of that. That's it. If E is not empty, let's go ahead and specify that the diameter of the empty set is 0. Just so we don't, just note that if E is the empty set, then you're trying to take the supremum of the empty set, to which we said the least upper bound of the empty set was minus infinity. We don't want the diameter of the empty set to be minus infinity. We want it to be, let's say for now it's 0. In some weird applications, you specify that the diameter of the empty set is a negative number or something equally bizarre, but why don't we just say the diameter of the empty set is 0? And let's talk about why this is called a diameter. So for example, if we take this circle here, we can take 2 points. We can find 2 points on this circle, like here and here, where the distance between the 2 points is the diameter. And then if you had another shape, such as this square here, the diameter in this case, you take the 2 points that are the farthest away from each other you can get, and that gives you the diameter. That's the diameter of the smallest circle that you can put around your shape. And let's state a fact. Cantor Conway, the author of your book, doesn't actually prove it. He thinks it's obvious, and it's pretty straightforward. But let's state it just so we've got just so we know what we're saying. E contained in the real numbers is bounded, meaning it's bounded above and below, if and only if the diameter of E is less than infinity. So the diameter of an unbounded set is infinite, and proof is pretty straightforward. Remember, E is bounded if it is bounded above and below. There exist real numbers A and B such that A is a lower bound and B is an upper bound, meaning that any element E of E is between the two of them. And then if E is bounded, then y minus x less than or equal to b minus a for all x, y, and e. And then because you can take them in either order, y, the biggest y can be as b, the smallest x can be as a, and then you can take them in either order, so you can take the absolute value y minus x and x minus y are less than b minus a, and conversely, if the diameter of E is finite, well, the empty set is obviously bounded, so E is not equal to the empty set. Then you just pick any E in E. Then E minus the diameter of E, that's less than or equal to F is less than or equal to E plus the diameter of E. F minus E is less than the diameter of E. E minus F is less than the diameter of E. And this is for all F and E. So E is bounded. Now here is a theorem that is due to Cantor, theorem 1.6.8. We will come back to this theorem in chapter 5, but it was originally proven by a mathematician named George Cantor. Let's let Fn be a sequence of sets. And let's suppose that the following four things are true. So the first thing we need to assume is that each of the fn's is a set of the real numbers. Second thing we want to assume is that none of them is empty. The third thing we want to assume is that is that each of them is closed. And the last thing we want to assume is that they're decreasing in the sense that Fn plus 1 is a subset of Fn. And we're going to assume these things are all true for all natural numbers n. That is, this is true for all the sets in your sequence. So if this is the line, then you can have F1, then F2 is inside that somewhere, then F3 is inside that, and so on and so forth. And the conclusion is that if at least one of the sets Fn is bounded, and that means that eventually they're all bounded. Fn plus 1 is contained in n, so Fn, so it's bounded. Fn plus 2 is contained in Fn plus 1 is contained in Fn, so it's bounded. Then the conclusion is that there is at least one point that's in all of them. If you intersect them up, you cannot get the empty set. And if you have a strongest condition, if you take the diameter of the fn's, that's a sequence of numbers. If that sequence converges to 0, then your intersection is a singleton set. So there is in fact exactly 1 point in the intersection. Let's go ahead and prove this. So let's let b be the natural number, be such that our f sub b is bounded. That meaning its diameter is finite, and we can also put a b be real numbers with f sub b inside this sequence a b. And I'm just going to point out to you, if you've got a number n that's less than b, then f sub b intersect ab. That's also known as f sub b. It's not empty, and it's contained in f sub n because this is a decreasing sequence of sets. So f sub n intersect ab. That's not equal to the empty set. And then for each natural number n, we're going to let x sub n, it has to be in the interval a b and also in f sub n. You don't need the interval a b if n is bigger than our capital B, but you do need it if n is less than our capital B, and we've just seen that there is such a sequence. All right, so now let us notice the following things. So first, the sequence xn n equals 1 to infinity is contained in this closed bounded interval. So by Bolzano-Weierstrass, there is a convergent subsequence let's call it set x sub n sub k. This goes from k equals 1 to infinity. And it converges to some number. xnk converges to x. Now, then the sequence, we're going to take our subsequence and we're going to throw away the first bunch of terms. xnk, we're going to start at k equals m. Then xnk, remember, if it's a subsequence, nk is increasing, so in particular nk is at least m. This is a so this whole thing, that has to be a subsequence of f sub m. And it converges we saw an exercise somewhere back in section 1.3 that if you take a sequence and you throw away the first bunch of terms, then it still converges to the same thing. So x is in f sub m because f sub m is bounded. And so the conclusion is that x is in the intersection of the f sub m's. And so that's the first part of it. And then we have this other condition. If the diameter of the f sub n's, if that is converging to 0, and we've got some point y that's in all of them, then the distance from x to y is less than or equal to the diameter of f sub n. X is in all the f sub n's, y is in all of the x sub n's, so x minus y, that's less than and equal to diameter of f sub n for all n. And then since that diameter is converging to 0, we must have that x minus y equals 0, so y equals x, and this intersection of all the fn's is the 1 point x. Here is a theorem that's actually quite useful. So let's let f be a closed and bounded subset of the real numbers. And let's suppose that we've got a sequence is a sequence of open sets such that f is contained in the union of all the GNs. And then it turns out that if the GNs are open, if f is closed, if f is bounded, then you can't actually need that many of them. Then there is always, it is always the case that you can do with just finitely many of them. There is a natural number n such that f is contained in the union from 1 to big N of Gn. So you can throw out all but finitely many of the GNs. And this is sometimes stated as every open cover has a finite subcover, and that this property is called compactness, and it's actually very important and very useful when we start generalizing, when we start getting to things more complicated than the real numbers. And let's go ahead and prove this. So let's let f sub n, we're going to take the closed set F and we're going to delete from it the first n of the n's, the GKs, we're calling them now. And then let's notice the following things. So Fn is certainly a subset of the real numbers. And then Fn is closed. And that's because F is closed. The union of the GK is open, but a proposition in 1.6.4 and that means that the complement of the GKs is closed, and F minus the GKs, that's equal to F intersect the real number, the complement of the GKs. That also has to be closed. This is again by proposition 1.6.4. So next thing to notice is that Fn plus 1 is a subset of Fn because Fn plus 1 is Fn, and then you take away Gn plus 1. And then taking something away is certainly, you're still going to be a subset. And then we'll also notice that Fn is a subset of F is bounded. The upper bound for F is also an upper bound and a lower bound for Fn. So that's most of the conditions of Cantor's theorem. The only one we're missing is that the Fn not equal to empty set. And in fact, what we're trying to prove is that one of the Fn's is empty. And now notice that the conclusion of Cantor's theorem is false. So by assumption, F is contained in the GKs. So every point in F is in one of the GKs. That means when you go through and delete the GKs one by one, eventually you're going to delete all of them. So that's the intersection of F minus the n's, and then we can apply some results from section 1.1, and this is theorem 1.1.8, then of course we don't really need to do this this double union. We can just take away the GK's once, not over and over, and then so the conclusion of Cantor's theorem is false. The Cantor's theorem says that if you've got this long list of hypotheses, then the intersection of the FNs can't be the empty set. The intersection is the empty set, so that means one of those several things that we assumed in Cantor's theorem has to be false, but we've checked most of them. So one of the hypotheses must be false. And the only one left we've shown that all the other assumptions are false, so the only one left is that Fn is not equal to the empty set. We've shown all the other hypotheses are true, so we must have Fn equals the empty set, and F is contained in the union from 1 up to n of GK for some finite n. And that completes the proof. The last concept that we want to introduce in this section is the notion of the closure of a set. So let's put down definition 1.6.10. So let's let E be a subset of the real numbers. Then the closure of E, we write that as CLE. That's the set of all real numbers such that the distance from X to E is equal to 0, where the distance from X to E, that's the E infimum of the distance from X to Y, where Y is a point in E. And here is a proposition. This is going to give us another way to look at the closure. So if you've got a set, then closure of E, that's the set of all points that are the limit of a sequence of points in E. So if there is a sequence of points xn and all of them are in E, and the xn's converge to X, then X is in the closure. And conversely, if X is in the closure, you could always find such a sequence. And here is how we prove this. So let's prove one direction first. Suppose that xn is a sequence of points in E, and xn is converging to x. Then the distance from x to E, that's less than or equal to x minus xn for all n. But definite, remember our proposition at the start of section 1.3. Yeah, by proposition 1.3.3, if epsilon is greater than 0, then there is a natural number n such that xn minus x is less than epsilon. Actually, this is such that xn minus x is less than epsilon for all little n bigger than big N, but this is one of those situations where you really need one of them, and this is true because xn is converging to x. So the distance from x to E is less than epsilon for any positive number epsilon. And then the distance from x to E, it's an infimum of absolute values. That means it's an infimum of negative numbers. So the distance is always non-negative. It can often be 0, but it can never be a negative number. So that means the distance from x to E is 0. X is in the closure of E. And so we've proven that every point like this is in the closure. Conversely, we're going to let x be in the closure of E. So that means that the distance from x to E is 0. So that means that the greatest lower bound on the set of lengths is 0. So if n is a natural number, then 1 over n is not a lower bound for the set of all x minus y absolute value such that y is in E. So that means one of these x minus y's has to be less than n. So let's let yn be in E with x minus yn absolute value less than 1 over n. And then it's pretty clear that yn is converging to x. You can work that out from the epsilon n characterization. You just pick your big N bigger than 1 over epsilon by the Archimedean property. You can do that. Yn is converging to x, and each yn is in E. And so we've seen that if X is in the closure, you can come up with a sequence that satisfies the property given in the proposition, and vice versa. If you satisfy the property given in the proposition, you're in the closure, and that completes the proof. So one more proposition regarding closures. So let's let E be a subset of the real numbers. And then we've got the following three things are true. The first is that the closure of E is a closed set. The second is that if E is a subset of F, then the closure of E is a subset of the closure of F. And the third thing, which I'm going to leave as an exercise, is that if E is closed already, then E is equal to the closure of E. So let me prove parts A and B to you. So first, part A. Let's prove that closure of E is closed by proving that its complement is open. So let's let G be Rn, the real numbers minus the closure of E. And our goal, what we want to show, is that G is open. So let's let X be a point in G. Then the distance from X to E. So X is not in the closure of E. So that means that the distance from X to E has to be positive. This next thing is a very general result about the distance function. So if E is any set of the real numbers and X and Y are both real, then the distance from X to E, remember that's the infimum of all X minus Z with Z and E. But that thing, you can turn that into X minus Y plus Y minus Z by the triangle inequality. Everything, all of these things, this thing is greater than or equal to this thing, so any lower bound on the first set is going to be a lower bound on the second set. I've only made my infimum bigger, and then it should be straightforward to see why this thing, since this X minus Y doesn't care which Z is, you can go ahead and move this straight on out. And you'll notice that that is precisely equal to X minus Y plus the distance from Y to E. So the distance from, so this distance to E function, we've got, if x and y are close to each other, the distance from y to E, it's at most the distance from x to E minus the absolute value of x minus y. Now, remember, we're trying to show that this set G is open. So let's let epsilon be half the distance from x to E. Let's suppose y is in this interval x minus epsilon, x plus epsilon. And recall, this is true if and only if the absolute value of x minus y is less than epsilon. Then the distance from y to E, that's greater than or equal to the distance from x to E minus x minus y. That's that whole S in orange with the x minus y moved over. But remember, this is the distance from x to E is 2 epsilon. So we've got 2 epsilon minus epsilon is epsilon, and it's pretty, and notice by assumption epsilon is positive. So the distance from y to E is positive. So y is not in the closure of E. So remember, G is the complement of the closure of E. So x minus epsilon, x plus epsilon is in G. And this is true for any Ex in G. So G is open. By a proposition we proved pretty early in this section. Then part B, if E is a subset of F and X is in the closure of E, then we've got some sequence that converges to X that is contained in E. But then that sequence of points in E, it's also a sequence of points in F. And so its limit must also be in the closure of F. One corollary I would like to mention and this is a corollary to it's B and C, which of course is left for an exam or study problem, is that if E is a subset of F and F is closed, then the closure of E, that's contained in the closure of F, but by part C, F is equal to the closure of F. So any closed set contains E also contains the closure of E. And part A, the closure of A is itself closed. So the closure of E, another way to define it, is as the smallest closed set that contains E. Smallest in the sense that it's contained in any other set that contains E.